Okay, I think we can begin now, right?
Yeah, you can start.
Okay. All right. Hello and welcome everyone to this webinar. My name is Stefan Habian and I'm a mechanical engineer here at Dante Solutions. I'd like to thank Santosh and Dihayo for organizing and setting up this opportunity to discuss heat treatment process simulations. Today's talk will be about the modeling aspect of heat treatment and how a simulation solution like Dante may be of benefit to you. A little bit about me. I've been with Dante Solutions for just under 2 years now. My main tasks involve the maintenance and development of the Dante interface to the commercial FEA solvers. Today's speaker and presenter is my colleague, Justin Sims. He's a lead project engineer here at Dante Solutions, and he'll be providing an excellent overview on Dante, who we are, what we do, as well as to present some of the heat treatment simulation case studies that we have available today. So in the audience, we also have a few of the other members of the Dante team, engineering team. But as I understand it, only the panelists are unmuted for this webinar. That's all right. But I do kindly ask that if you have any questions, please feel free to post them in the chat box, in the comment box below. We'll be monitoring for questions throughout the presentation and providing feedback. For a long time, our focus, our expertise has been in heat treatment modeling and simulation. So we very much are interested in knowing what some of your concerns and needs are. So if there's any specific topics that you'd like us to address, please let us know through a comment. Also, feel free to contact us, check out our website for more info and case studies, or inquire with Santosh at Dihayo. That said, I'm going to hand the floor over to our presenter, Justin Sims.
Good afternoon, everybody. Yeah, so my name's Justin Sims. I've been with Dante about 6 years now. My main responsibilities over at Dante are mainly consulting service work, so the modeling side of it, software training, support, and I do help with the development from time to time, mainly with testing and stuff in that nature. And as Stefan mentioned, if you guys do have any questions or anything, yeah, please add them to the chat. Also, half this presentation is who we are and what Dante can do. The other half is case studies. So if you guys have any particular interest in certain processes, try to let us know early in the presentation, and I can kind of try to dwell on those case studies a little bit more. There's a lot of slides here, so without further ado, we will get started. So this is heat treatment process modeling using Dante simulation software with case studies. Get on the right screen here. Okay. So a quick outline, who we are as a company, and then introduction to our software. We also have additional Dante capabilities that are available within our models, and then some interesting case studies, which include induction hardening, press quenching, carbide formation, oil quenching, high pressure gas quenching, decarburization, and then using residual stress in loading models to predict part service performance, and then a quick animation of a butt welding process. And we'll wrap things up with a quick overview. Also, we have some Dante utilities available to help evaluate material and also to get material parameters into the Dante model from experimental results. We'll go through those kind of quick though. So brief introduction to who we are. Dante Solutions was founded in 1982 with a main focus on modeling thermal processes, and in those early years a lot of it was on the forging simulation. However, in the early 90s, Dante Solutions was brought into a large collaborative project between industry, academia, and our national labs. And the purpose of this was to predict distortion in heat treatment. And this project ran from 1992 to 2000. So it was a long project that really tried to nail down the physical phenomena of heat treatment and the resulting distortion. And this was brought about because of industry having such a difficult time with heat treat distortion and the amount of money that they were spending in scrap. So Dante Solutions then became the sole owner of the Dante software in 2000, and we've been responsible for the development and furtherment of the software since then. And a lot of work has gone into the models, the algorithms, and the material data. So this has been a 20-year adventure, we'll call it. Originally, the name was Deformation Control Technology. So if you see any papers or publications from prior to 2014, you might see that name associated with our employees, particularly Lynn Ferguson and Charlie Lee. Also, we had an employee that did a lot of publications back in the day that was Andy Freeborg. So any of those guys, if you see their names on papers with Deformation Control Technology, that's us. Dante actually stands for Distortion Analysis for Thermal Engineering. So it is an acronym. And our main lines of business are first and foremost the software licensing, followed by heat treatment technology development. And we've done a lot of work with gas quenching and press quenching in aerospace industries in particular. And then finally, our consulting services, either for those companies that don't have the analysts to run simulations, or they just have one problem they'd like to solve and don't want to invest in the software itself. However, we highly recommend that if you have one heat treatment problem, you most likely have more than just one. So generally the software is needed throughout the company, even if it's not quite realized. All right, so some quick project references. We do a lot of transmission shafts and gears, and a lot with the aerospace industry because their tolerances are so tight. We've done obviously thermal stress and metallurgical analysis of quench hardening, and that's liquid quenching, gas quenching, even salt bath quenching. We've looked at quantitative measurements of steel transformations using dilatometry, cast rolls in the steel producing sector. A lot of induction models lately. We don't model the actual electromagnetics, though we can predict the stresses and strains from the process itself, but I'll get into that with some examples later on. We've looked at normalizing processes to improve them, bearing rings, gas quenching distortion of aerospace gears. And the last one is we actually recently designed a innovative gas quenching method that we've tagged Dante Controlled Gas Quenching, that actually controls the temperature of the incoming gas to control the phase transformation gradients. And it's a great means to reduce shape distortion. So the actual non-uniform transformations that occur during gas quenching. You can't get rid of the size change from going to martensite, but you can get rid of shape change. All right, so these are a few of our parts that we've modeled. Like I said, lots of gears, lots of shafts, crank, crankshafts, induction, particularly looking at oil holes and the stresses that arise around oil holes due to temperature increases. Some of our customer references. So you can see here lots of aerospace, Avio and Bell and Boeing, Liebherr, Sikorsky. And then we get into the automotives in Chrysler and Ford, GM, Hyundai, a lot of the big name guys, and then heavy equipment manufacturers, Cat, Cummins, Deere, all very big names. And then some heat treaters, and then our universities that use our software. And we work a lot with the universities as well. All right, so what is Dante heat treatment simulation software? So it is a commercial finite element based software that is used with ANSYS or Abacus. So in order to use Dante, you got to have ANSYS or Abacus. And we did this so we did not have to focus on the actual solving. So there's great solvers out there, and those folks have put in a lot of work and effort to optimize their solutions. So we just use their ready-made solutions for the solvers. And most engineers are familiar with Abacus or ANSYS, so it's kind of a streamlined transition to start using Dante. And I was going to try to show some quick examples, but I just found out that my license for Abacus expired this morning. We're all still working from home, so I have to borrow licenses, and yeah, it's expired. So I'll try to do something, but I can't promise anything at this point. That's kind of my fault. I apologize for that. But our heat treatment process capabilities. So essentially, if it's a heat treatment process, Dante can model it. Carburizing, low pressure and gas, nitriding, all forms of heating, immersion quenching, gas quenching, just straight air cooling. Then you get into the forced sprays with spray quenching, intensive quenching. We can model the press or fixture quenching, so external loads during the process, no problem. Induction hardening, like I mentioned earlier, we don't model the electromagnetics, though we can take the Joule heating from an electromagnetic model and use it as an input, or we can do it manually and figure out what the Joule heating profile is. Both ways have worked phenomenally well in Dante and in outside companies. Any deep freezing or cryogenic treatments we can handle, low temperature and high temperature tempering and normalizing. And then Stefan, I see we got like a couple comments. I don't know if just one or something, but if you want to keep an eye on that, and if for any reason you need to interrupt me so we can answer a question, do that.
Yep, sounds good.
Okay. So what is required of an accurate and practically useful heat treat modeling? So in the figure on the right, you can kind of see these three boxes are what we need to consider: heat transfer, deformation, and phase transformation. The solid lines are absolutely critical: latent heat, transformations, the volume changes, and the thermal expansion. The dotted lines are less important. We do have models for them, though generally we don't use them mainly because the deformation's small, and particularly the heat generated by plastic deformation isn't needed. However, if you do forging models and you want to include the transformation after cool down, then it should be used. This is particularly important for like sheet metal stamping and stuff like that. Like I said, we need phase transformation, multi-phase mechanical, trip models. Got to have a mixture law in there because you can have elements that are more than one phase at the same time. And then tempering models, as well as carburization and nitriding models. So all of this must be included to accurately model a heat treatment process. Heat treatment modeling is probably one of the most complicated phenomena to model because of the wide temperature range and the wide range of solid state phases that are possible. So there's a lot to consider in here. This is why we've been developing it for ongoing now for the last 30 years. So Dante function structure. So everything we do here is heat transfer driven. and generally we use heat transfer coefficients. Flux can be used, but it's a little bit harder to know exactly what the outside environment conditions are when you use flux. So we use heat transfer coefficients. Diffusion, phase transformation, mechanical models, all of this is included, as well as a standard database. So if you're using a common grade of steel or one that's reasonably close to a common grade of steel, and I know India uses different standards for steel than America, but generally they're really close. And then also there's a custom user material, so we can add a custom material that is specific to your company, so we don't have to share that with everybody else. That's if you want to do the testing and fun projects to get everything fit, or you can do the fitting yourself, but there is that capability to have your own material data for your specific grade of steel. Finite element based, and then our outputs include volume fraction of phases, dimensional change, residual stress, and hardness. And everything except for hardness, because it doesn't make sense, is predicted in process. So you can see the changes as they occur, so you can see where your problems happen, or when the good things happen, right? So it's a very powerful tool in that regard. You're just not getting what happens at the very end, because you can measure that physically. It's what happens during the process that we're really concerned about here. So that's where Dante is a very powerful tool. Our file structure here real quick. We got our user subroutines, and as I mentioned, you got to have ANSYS Mechanical or Abacus Standard to link with. There's a small processing database that has generic heat transfer coefficients for oil quench, air cool. I think there's a water quench in there, oil. So there's a couple of furnace heating. So there's a couple of generic data sets to start from. If you don't know your system behavior, we can at least get in the ballpark, at least get close. Then we have our material database. I think I got a figure of in the coming slides that shows some of the steels we have. Then we have a bunch of examples so you can see how certain models are set up, some tutorials that go step by step in setting up some simple models, and then our help system. Like I mentioned, we also have some utility tools available. All right, so the way that we normally run these is we sequentially couple them, which is the figure on the left. So we'll run a carburization model and get a carbon distribution. That carbon distribution will then get mapped to what we call a thermal model, which will be the process, the actual heat treat processing steps. That'll get us our temperature history, which is then read by the stress model, which gives us the distortion, residual stress, and microstructure. So it's a three-step process, and because the distortions are small, it's possible to do it like this. If the distortions are larger, like for hot stamping, then you can couple the thermal and stress, but it generally takes a little bit longer to run, but the accuracy is better. And if you have large deformations, it's necessary because the thermal properties can change a lot quicker. All right, our models. Below on the left is our general form of our phase transformation models. For obvious reasons, I can't put the full model here, but it can be determined from dilatometry or TTT diagrams. However, we do prefer dilatometry data because it provides diffusive and Martinsitic phase transformation information. It provides the coefficient of thermal expansion and the transformation strains. So we get a lot of information out of one test, whereas the TTT diagrams just get us the diffusive transformation information. There's nothing about martensite except for a start and a finish temperature generally, and there's no thermal expansion or strain information at all. So we just, if it comes from TTT diagrams, we just assume something close and we borrow that strain. So we can get reasonably close, but it won't quite be accurate. So dialectometry is the way to go if you're going to measure phase transformation behavior. The figure on the right, upper right, is our representative of our internal state variable model. And we use an internal state variable model instead of the classical stress-strain relationship because it captures the hardening and recovery that happens during the process. And that's not possible with a conventional stress-strain relationship. So the internal state variable model handles all of that. There's like 27 parameters involved in this model. So it is extensive. And the properties are all functions of phase, carbon, temperature, strain, and strain rate. And it also includes a mixture law. So there's a lot going on there. It's a great model. It works really, really well for heat treatment modeling. Very well. All right, so here's our material database. You can see some of our standard materials. Any of these materials that have an XX at the end indicate that there's multiple carbon levels data. So the carburization process can be modeled more accurately because carbon has such an effect on material properties. It has to be considered. So we can see 4000 grade, 4100 grade, 4800, 5100, 52100 bearing steel. So it's just got one carbon level in it. 86, 9300. So you can see the common grades, especially to aerospace and automotive. But inside of that material data then is phase transformation properties, thermal and mechanical properties, carbon diffusion, nitrogen diffusion properties, and also microstructural and alloy effects are all included in these material properties. So this is a big deal because it's a lot of data for each material that has to be tested for. So to have this coming in is very helpful. And like I said, if you're close to one of these, and this isn't all of them, there's more, I couldn't fit them all here. If you're close, then generally we can make some small modifications to the hardenability if it leans one way or the other relative to these alloys, and at least get you close without doing any testing. And then you can do some minimum testing to kind of fill in the blanks. So starting from here, a lot less testing involved. All right, thermal boundary conditions are absolutely critical, and each system will behave differently. Even identical equipment models will behave differently. It's just a fact of nature that every heat treater has to deal with. So we highly advise that vessels be characterized. So heat transfer coefficients as a function of part surface temperature should be tested for and determined. We do offer advanced support for that, and we have done a lot of testing as far as heat transfer characterization goes. So we are very experienced in this. So then we must also consider, particularly between the two different quenching methods, liquid and gas, there are some differences that you must consider, right? For liquid quenching, you have to consider the vapor phase, the boiling phase, and the convection phase, represented by the figure on the bottom left. These are as a function of part surface temperature. So when the surface is really hot, you're in a vapor, slower heat transfer. And then as your vapor breaks down, you get to nucleate boiling, which is your highest heat transfer. And then you slowly go down to pure convection. For gas quenching, you have to consider the ambient gas surrounding the part. So this shows if you took a part out of a hot furnace and stuck it into a cold gas chamber, this is the temperature of the gas around the part that essentially drives the heat transfer. So you can see as the part enters the chamber, it gets heated up. And then as the gas is cooled by the heat exchanger, the gas eventually around the part drops back down to the ambient. So all of these have to be considered. And the key to all of this is you want to test your actual process route. So make sure that your temperatures and your times are representative of your process. You want to use the equipment that you're using. Don't test this, testing fluid in a beaker in a lab is good for quality control. It's not good for heat treatment modeling. It'll help, but it's not what you really want. What you really want is your actual equipment, and then obviously the actual material that you're using. However, the material testing for heat transfer is helpful. However, stainless steel works really good also, austenitic stainless steel, because it doesn't go through a phase transformation. So there's no change in thermal properties. So a lot of times we'll use stainless steel, but these first two are absolutely critical, using the actual process and the actual equipment. All right. Like I mentioned, heat transfer coefficient, bunch of different ways, characterization, bunch of different ways to do it here. We can do it with quench probes. So this cylinder is fitted with thermocouples, and it goes through the process. You can see the umbilical cord coming out. We can actual part. So these are a big work roll that got thermocouples, little bearings. We actually did a landing gear. I'll show you on the next slide. And you can also use computational fluid dynamics as well. We don't like taking the heat transfer coefficient straight from CFD because it's so hard to capture the phase changes of liquid and their effects. There's a lot of good work going into it right now, so I have hopes that it'll come along in the next couple years. But for right now, we just prefer to use velocity profiles, so you can kind of see where we get faster flow, where we get stagnant areas, things like that, and then use some good engineering judgment to determine the heat transfer coefficients. So this was a large landing gear, thermocouples. They're welded on the surface. We actually prefer to get them embedded just a little bit, but this works. Then we build a model and kind of fit the heat transfer coefficients from there. This was a high pressure gas quench where we were looking at different positions in the chamber. So these cylinders getting put in different positions, different locations around the cylinder, how the heat transfer varies there. Locations in the rack, different load configurations, and different load sizes. So this was an interesting study, and this is data from there, and you can see the difference. These are the thermocouple temperature measurements that go around the cylinder. So you can see that there's difference circumferentially due to the gas flow. You can also see the bump here. That's from the latent heat during assumed ferrite perlite transformation. We can skip this. You guys, I'm pretty sure he shared this. You guys can read this just really quick, what the difference between gas and oil and what needs to be considered. But I want to get through some of this other stuff. All right, so other Dante capabilities. So we can consider the alloy composition on phase change. So this example shows if our molybdenum goes from 0.2% to 1.2%, you can see the shift in the ferrite perlite and the bainite noses. So everything goes to the right. So essentially makes it more hardenable. We can also consider the effect of austenite grain size. So this grain size is in millimeters, so we're from 63 microns to 163 microns. Again, you can see the shift to the right. So larger grains make it more hardenable. The effect of initial phase on phase transformation. So the first cycle here is annealed condition, most likely ferrite perlite. And then this blue line is the retest of the same sample after being quenched to martensite. So this blue curve starts as martensite. And this volume shrinkage that you see here is actually the material being tempered at high temperature. And then you can just see the effect on the transformation strain and the total strain from the austenite transformation. So depending what phase you start with, you're going to end up with different strains. And this shows it really well. So the blue line is starting with perlite. These are all simulation on this figure. This figure was actual test data. So this figure is all simulation. The second is high temperature tempered martensite, and the gray curve is low temperature tempered martensite. And you can see they all start at the same place, but they all end at different places. So the start of the initial phase is absolutely critical. So it is really important to know your initial material structure, phase, grain size, alloy composition. All that's very important to know. Also, we can model the effects of initial carbides on phase transformation, and it affects the phase transformation, right? Because your carbon, all that carbon that dissolves from the carbide then goes into the surrounding austenite matrix, which raises the carbon of the austenite, which then increases the hardenability. So these top left and bottom two all show 850 with a medium size carbide, small carbide, and large carbide. And you can see, so this is the carbon going into austenite. So you can see that the small carbide dissolves really quick, whereas the large carbide dissolves very slowly and doesn't even fully dissolve in this time. And then this is the medium carbide size figure on top right at 950 instead of 850. So you can see we go a little bit quicker at higher temperature dissolving. The effect of ferrite forming, also same as kind of with the carbide. As we form ferrite, we reject carbon because ferrite can't hold very much carbon in solid solution. So that carbon then goes into the surrounding austenite matrix, which then increases the hardenability. So we can consider all of that. And we can also consider the effect of precipitate growth coarsening and their effect on material property and volume change. So we describe it as a size function. So your probability of having carbides of this size essentially is what this curve says. So as time goes on, you essentially get higher and higher carbon and carbide. So the bottom is going to be the carbide size. And you also shrink as your carbides coarsen. All right, so that basically goes through the Dante portion of it. I guess we can go through the slide here real quick, and then we get into case studies. So this is the effect of phase transformations on distortion. All right, so there's two places we get distortion from in a heat treat: thermal stresses and phase transformation. And we hear a lot of it's all thermal stresses, and I'm here to tell you it is not all thermal stresses. So this is just a model, but this clearly shows that without phase transformation, we get 900 microns of shrinkage. As we expand the martensite, and you can really see it in this curve, as we expand the martensite, it reduces the shrinkage substantially. Right, 740 microns is huge. So, and that's looking at this point down here on the spline. And if we plot the top portion of the inner bore and the bottom portion of the inner bore on the bottom, you can see the difference. You get the same shape, essentially, but it's tremendously different in the amount of radial displacement. So phase transformations do make a huge difference in the final distortion. Huge difference. Okay, so that is it for the Dante portion of it. Okay, I don't see any messages or anything. So I'm just going to kind of run through these. We're already about a half hour in, so I think I kind of want to get through this about 20 minutes or so, and then if we got any questions, Stefan and I can answer, and I see Dan's there too. So, all right. This example is induction hardening of a 1541 axle shaft. It's about 1 meter long, 35 millimeter diameter with flange on one end and a spline on the other, with cracking occurring in the center line down here near the flange. Our model's down here on the bottom, assume cyclic symmetry, And this meshing here is representative of what is needed of a heat treatment simulation mesh. Really fine near the surface to capture the steep thermal stress and phase transformation gradients. And then it can get a little coarser in the core because the gradients kind of decrease. So this particular model, the electromagnetics were actually modeled by Fluxtrol using Flux 2D. And then the power density, so the Joule heating as a function of time and position, was mapped into the Dante thermal model to predict the temperature history. Once we have the temperature history, then we can run the stress and get the displacements and the residual stresses and the hardnesses. The Joule heating can also be defined by the user based on actual component case depth and microstructure. And by doing that, that then gets us a baseline of this is what the process does right now. We can then use that to modify and see how we can improve or optimize the process. So we can play with power levels. So what happens if we put more power to it, less power? You can essentially manipulate the frequency by modifying how deep the Joule heating goes. Right, because frequency essentially dictates how deep your electromagnetic waves get to inside the part. This process, it consisted of a 9-second dwell at the flange to let the thermal energy build up. The inductor then moved up the shaft and then slowed as the spray quenching began. And then the inductor was shut off once it got near the top to allow to keep the end from cracking. So this is an animation, left to right. We got temperature, austenite, martensite, axial stress, and axial displacement. So you can see our austenite formation as our inductor moves up, our martensite formation as the spray follows, and you can see this interesting tensile spike that runs up ahead of the inductor. You also have high tension in the core, which balances the compression from the martensite transformation. But this tensile spike that runs out ahead of the inductor is the reason that you can crack the end of the shaft if you don't shut the inductor off. I'll let this run through just so everybody can kind of, I know it's a lot to take in with being 5 figures. But so this is a scanning process. All right, so we can so what we ended up doing for this was we wanted to see the effect of quench rates on the stress. And following intuition, the lower quench rate reduced the stress. So you can see up here 5 kilowatt meters squared C, drops us down to about 700 MPa in the core, where if we go with what they were actually running was 25 kilowatt meters squared C, and you get a tensile spike of about 820 megapascal down here. Granted, your surface compression is a lot more, but if you can't stop cracking, it doesn't matter what your surface compression is, right? If you're cracking near the core. So had to reduce the tension. So that's kind of what ended up occurring, was they just reduced the pressure in the spray to kind of reduce the heat transfer coefficient. So this is single shot induction of a crankshaft. Now, most of these single shots are still essentially rotated, but generally the rotation rate is such that the temperature should remain uniform in the circumferential direction. So generally we ignore the rotation. However, if you really feel the need that your rotation is messing up the process, it can be modeled. So this is on the left is a temperature distribution at the end of heating, right before the spray quench starts. And this shows the 2-step heating process that was involved. So these are just still shots of martensite on the left, hardness in the middle, and our residual stress on the right. And what ended up happening was this oil hole got redesigned because it was too close to the bottom bearing surface down here. And you can see this tensile spike that you don't have up top. And it's all because this hole is closer to this bearing surface than to the top bearing surface. So it's very interesting. All right, so press quenching of a 52-100 bearing ring. So about 4-inch OD, so about 100 millimeter OD. There's top and bottom constraints. So you can see the model on the right. So you have a top die, bottom die, and then the expander on the inner bore. All of this was per Gleason practice. So we worked with Gleason on this. They're a manufacturer of heat treat equipment. Do a lot in press quenching. They were getting almost 60% failures from the original process without pulsing. So pulsing essentially allows the relieves pressure of the upper die, which then allows the part to shift. Without releasing the load on the upper die, it constrains the part too much. And this is something that we wanted to look at. So what we wanted to look at mainly was we wanted to be able to predict that location of high in-process stress and see where and when it was cracking. And then we wanted to determine what the effects of friction and quench flow rate were on this stress. So you can kind of see our table of simulation experiments over here on the right. All this was simulation. We used standard press quenching to evaluate a few different friction coefficients, 0.5, 0.2, 0.5. Then used our 0.05 friction to evaluate a few different flow rates. We then looked at what happens if the top and bottom dies stick, and what happens if the top die sticks by itself or the bottom die sticks by itself. So the sticking essentially shows the no pulsing, because if you keep pressure on the part, you're likely to hold it into place, which would essentially be a sticking situation. So the part refuses to move. As you thermally contract it, it does not contract. As you expand a martensite, it does not expand, at least on the surfaces in contact with the die. So here is an animation. From left to right, we got max principal stress, temperature, and martensite. And our area of concern here is on the bearing race. And you can see it right there at the end. You can see it happen right at the end. It goes to red. But the reason for it is the martensite transformation in the core tied to the fact that these dies, this is actually a friction condition. And you still get a high stress over there. But it's because the martensite transformation in the core goes. Once that happens, it pushes everything out and actually tries to open up the bearing race, which puts a bending moment on the bearing race. This is just a quick plot showing stress from if you have a low friction press quench compared to a immersion quench or a free quench without constraints. So you can see the effect of the constraint and the friction. This also has to do with the slightly higher quench rate as well. So there's kind of two things going on here. But we can show all of that, right? So these two lines are temperature. The dotted lines are martensite transformation. And then these squares are the stress. So we can see, you know, where it comes from, right? Here's your martensite transformation. but your stress and this is all just at the surface. So you have to keep in mind that it's not the surface stress that's causing this, the surface martensite transformation that's causing this stress. It's subsurface martensite. So you really need a couple more plots on here to really drive home, what the cause is. All right, how are we doing on time? At 15 minutes roughly. All right, so press quenching 9300 is just another press quench model. The main thing to take away from here is we can locate the dies. If there's a gap, like the bottom was shimmed, right? Then we can model that. Carbon profile, I don't think we've seen up until now. So there's a carbon profile. This was an interesting study that I want to talk about just for a brief second. So what happened here is that this is the top portion of the bore, so it's this portion, and this is the spline down here. So the blue line is what would happen without constraint. So if I just dumped this in an oil tank, this is the prediction. The gray line was the process that the customer was currently using. And you can see, especially on the spline, it actually made the distortion worse. So their thought was, by constricting it, I'm going to make the distortion better, but in reality, they were making it worse. So what we did was we came in and said, okay, forget the expander, which essentially puts a load on the bore. And we said, use a plug, which is a solid cylinder that goes inside of the bore. That's the green line. So we reduced the distortion of the bore substantially. However, we end up with this big taper. So what we said was, okay, well, we can get rid of a taper by using an inverse taper. So we essentially reversed the taper in the plug. By doing that, then we force it to be straight. We ended up with which is this brown line. We end up with a little bow now, which isn't bad. I mean, that's still pretty small. That's 10 micron, 5 micron, or sorry, about 20 microns. So that's relatively small. The customer was ecstatic. They were actually okay with the taper. But anyway, so then what you can do is you can essentially, like you did with the taper, you can make an inverse contour and try to remove the bow shape here. And it sort of worked, but it sort of didn't, especially on the spline. So with that in mind, we said that it wasn't worth to do the contour, but it was definitely worth to do the taper and the plug. So you can, and this would have been months and months of machining equipment for the press quench and making the parts and measuring the parts and running the trials, where in simulation I could do this in a day. So it's an extremely powerful tool to get you, even if your conditions aren't exact. So your accuracy isn't exact, but you're close. You can still see these trends, right? So what if this is actually, an extra 10 microns over, right? You see the trend, and that's a very, very powerful tool. So you still might have to run a couple experiments to really dial it in, but you've just eliminated like a dozen previous experiments that would have been complete failures. So it's like I said, very powerful. Carbide formation. This is huge, especially for high alloy steels. You cannot model the carburization, a low pressure carburization of a high alloy and some medium alloy steels without considering carbide formation. Why is this? Because as you pump in carbon, you saturate the austenite, and then you start to form carbides. Those carbides grow. So our plot on the right shows The blue lines down here are carbon and austenite. The gray line is the carbon that is in carbide form, and the orange line is a combination of the two. So you can see we build a carbide up. That carbide then dissolves during the boost stage. So low pressure carburizing is I boost, I give it acetylene, which is a carbon source. I give it a couple minutes, and then I suck all that acetylene out to a near vacuum, and I let the carbon diffuse, reducing the surface carbon. I then put acetylene back in, let the carbon build up, suck the acetylene out, so it's a repeating process. And as the carbides dissolve, they provide additional carbon to the matrix, right? So you have to consider them, or else you're under predicting the amount of carbon and the case depth that is actually there. So Dante has this ability. This is just a still shot. Let me think about getting an animation in here now that I look at it. Anyway, so on the left is the overall carbon. So you can see we're almost at 2% in the corners up here. The figure on the right is the amount of carbon that is in carbides. And you can see we got about 1% in the tip edge, about 0.5% everywhere else up on the tip. And then as we go down, we substantially lose carbides. So light carbides down here on the flank and in the core, but a bunch up here on the tip. All right, oil quenching of a landing gear. I want to go through this really quick. Just mainly show the animation, but we were looking at bow distortion of this guy, and this is a really big, several meters tall. I mean, this is a really big landing gear. So the immersion process into the oil is a big deal, right? As this gets dumped down into the oil fills up the hollow tube in the bore, and it also fills up this tube out here. All of this is very significant. So Dante can model that immersion process. Smaller parts, that immersion doesn't matter. It happens so fast that you can consider everything uniform. But with long parts like this, you have to consider the actual immersion of the part into the oil tank. Skip over that. So this is left to right, temperature, austenite, and radial distortion. So horizontal distortion. And you can watch with the temperature. So here's the oil filling up the bore. It fills up this tube a little bit faster was our assumption because of the pressure. So it fills it up. So this is looking inside. These are all on the outside. And then one more, a couple more here. So we can handle multiple materials. That's basically what this says. And the effect of welding two separate materials together is very significant, which I'm sure most of you know. So we can handle that. High pressure gas quenching. We've done a lot of work with high pressure gas quenching. There's a couple examples of different high pressure equipment, multiple chambers and single chambers, and we'll get into that. So we looked at some ring gears, and particularly of significance was the out of round distortion. So this thing was becoming like egg shaped. It's not, you can't see it physically, but it's turning egg shaped. What they were doing was they were trying to manipulate the quench by manipulating the fan speed and the pressures, which then essentially just affected the heat transfer coefficient. So Dante had no problem modeling this. You can see a couple of the experiments that we ran, but these are differences around the ring itself. So there was a lot of temperature non-uniformity going on here. And you can see in the figure on the bottom left from the simulation that there's up to 150 degrees Celsius difference within the ring, which leads to significant distortion. because your martensite transformation is starting over here and like 70% complete over here in the core, where over here it's 0. This little bit around the outside is insignificant to the overall distortion. It's this bulk core material that's going to drive the major distortion. And the interesting thing is, even though it's hard to see, and this is still magnified 50 times, but it's hard to see. Even though this is out of round distorted, the residual stress is still perfectly uniform. So it has nothing to do with non-uniform residual stress and everything to do with this non-uniform transformation. So it's seeing stuff like this where that gas quenching process I mentioned at the beginning, our controlled gas quenching process, comes into play. So using simulation, we can essentially design the recipes to mitigate, to reduce this behavior here on the far right and the left. I mean, it's essentially saying the same thing. Temperatures on the left, martensites on the right. So big deal. Decarburization we can model. So this was peeling of a gear. Just looking at decarb. Without decarburization, we predicted a high compressive residual stress, and there was no reason this thing should be cracking. It was cracking during the final grinding process. You can see as they ground it, it would start peeling. So we predicted all should be good and it should not crack. So we looked at what happens if this thing is decarbed 0.1 millimeters. And then we predict a shallow surface tensile stress, which would cause the peeling. And this is shallow. This is only, this right here is probably about 100 microns maybe. So it's not too deep, but it is there. It says the tensile stress goes 300 microns. I just want to show this real quick. We're running out of time here. These are test gears that we were modeling and using different processes to induce different residual stress magnitudes. And this figure shows on the left a loaded gear, so it's loaded out here on the tip. If it's loaded without residual stress, we end up with a tensile stress of about 700 MPa in the root fillet. If we do include the residual stress from heat treatment, we're still in compression. So we're not going to, I mean, it's completely different scenarios here. The one on the right says we will never fatigue out here because we never go tensile ever, where our mean stress is compressive. So right, how do you fail? So Dante can be used for that. So if you're running loading models, the residual heat treatment stress from Dante can be mapped into your loading models. This was one we looked at that had a internal flaw, big, huge steel work roll. So we predicted high tensile stress in the location, but it took an internal flaw to actually make it crack. It wasn't that high. Quick. This is butt welding. There's still a lot of work going on as how to model welding and additive manufacturing processes efficiently. It can be done. This kind of shows it, but this isn't the most efficient way to do it. So one of our colleagues, Charlie Lee, has been doing a lot of work with this lately. So hopefully we have some good progress here over the next year or two, as far as, and ANSYS and Abacus are also working on this problem of how to model an additive manufacturing process laying it down layer by layer. Some of our utilities here really super quick. So we have G-carb and V-carb, which are used to model carburization processes and to help design recipes for carburization processes. Material simulator, which will use user-defined heating and cooling curves to predict phase, hardness, strain. So it's a good way to get a quick feel for what a material's doing. TTT generator, which will predict and display TTT diagrams and also CCT diagrams from Dante Materials. Jomini predictor, kind of self-explanatory there. CHT generator allows for the evaluation of isothermal and rate-based austenite transformation behavior. A lot of work has gone into this area over the last year or so. Generally, we had been ignoring the rate-based austenite transformation because there's so much going on the cooling side of it, but we feel that the rate-based austenite transformation deserves more work, and so we've been putting a lot of effort into this, and I think it's come along quite nicely. So this little utility will kind of let you evaluate how the material behaves as far as that the austenite transformation goes. So all of those were predictive. These last ones are fitting tools. So the previous ones can all essentially be used on their own without Dante. However, the fitting tools don't make any sense unless you have Dante because they fit material data, fit material test data to our model parameters. All right, so Dial-A-Fit takes dialectometry data and fits the austenite transformation to all the diffusive phases and the martensitic phases. MechFit takes standard compression tension tests and fits them to our internal state variable model. Then we also have a TTT fit and a heat transfer coefficient fit, which use TTT diagrams to fit the phase transformation behavior, and then HTC fit uses thermocouple data to fit the heat transfer coefficient. Both of these are currently being worked on as far as graphical user interfaces go. So they're still available. Everything just has to be done through a command window and applied in Excel for right now, but they're on their way. So that is it for the presentation. We're basically out of time. So I don't have the ability to show a quick demo because my Abacus license is acting up, and we're just generally out of time. I don't want to take up everybody's time, so I'm going to pass this back to Stefan or Santosh, and they can kind of wrap things up. So I appreciate everybody's patience. And if you guys have any questions, feel free to ask them in the comments or to send any of us emails. We're more than happy to answer questions. And thank you.
All right, thanks, Justin, for that presentation. Yeah, it doesn't seem that we have any questions, but if anyone has anything, we can stay on for a bit longer. Just type it into the chat. And yeah, thank you for attending. Yeah, I know this meeting was scheduled for, I believe 3:30 to 4:30 your time. So I think this would be sort of the end of it. So I don't know, Santosh, if you want to, we can end things here now if there's no more questions.
We seem to have lost Santosh.
Yeah. Thank you, Justin and Stephen.
I see.
I
Yep,
thank
you're
all
very
the
welcome.
participants who have attended this workshop. So you have the email ID. If you have any questions and queries, one can just shoot the email to us. We'll be able to answer those questions or clarify those doubts. So thank you one and all. I'll be closing the webinar, ending the webinar.